Hello, my name is Yonatan Rosenbloom, and today we will be going over my individual technical presentation for Capstone 2. So, without further ado, let's begin. So, I will be discussing the steps for feed-forward neural networks. Real quickly, feed-forward neural network are a type of artificial neural network where connections between nodes do not form cycles, meaning that the information travels in one direction, forward. So first we have the input layer. So there are 5 steps. So first we have the input layer. That consists of neurons, with each neuron representing a feature or dimension of the input data. Then we have our data pre-processing, which is prior to feeding the data into the neural network. Pre-processing steps such as normalization or standardization may be applied to ensure that the input data in a suitable range and format. Normalization scales the input data to a range, typically between 0 and 1, making it easier for the network to learn. Standardization transforms the input data to have a mean of 0 and standard deviation of 1, which can improve the convergence of the training process. Thirdly, we have feature encoding. Categorical features may be encoded into numerical representations before being passed into the neural network. Techniques such as one-hot coding or label encoding can be used to convert categorical variables into a format that the neural network can understand. Fourthly, we have passing data to hidden layers. Once the input data is pre-processed and encoded appropriately, it is passed forward to the neurons in each hidden layers through the weighted connections, and each neuron in the hidden layers receives input from all neurons in the previous layer and computes a weighted sum of these inputs. Fifthly, no computation beyond passing data. Unlike the hidden layers and the output layer, the input layer does not perform any computation beyond receiving and passing the input data. The layer simply acts as an entry point for the data into the neural network, transmitting it to subsequent layers for pre-processing. So next we have our hidden layer. These perform the essential task of processing input data through weighted connections and activation functions. So let's begin. First, we have the weighted sum calculation. Each neuron in the hidden layer receives input from all neurons in the previous layer, which could either be the input layer or another hidden layer. The input is received by each neuron, a weighted sum of the outputs of the neuron in the preceding layer, where the weights represent strength of connections between the neurons. Second, we have the activation function. After calculating the weighted sum, each neuron applied in the activation function to introduce nonlinearity into the model. Common activation functions include the sigmoid function, the hyperbolic tangent function, and rectified linear unit, ReLU, and its variants. Thirdly, we have the nonlinear transformation. The activation function transforms the input received by the neuron into its output. This introduces nonlinearities into the model, enabling it to learn complex relationships in the data. Without activation functions, the neural network would essentially be a linear model, incapable of learning nonlinear patterns. Fourthly, we have the feature representation learning. As data passes through the hidden layers, the neural network learns to extract and represent increasingly abstract features from the input data. Each layer captures higher level representations of the input, potentially encoding more complex patterns and relationships. Fifthly, we have the depth and width impact. The number of hidden layers and the number of neurons in each hidden layer, known as the width of the network, significantly impacts the network's capacity to learn complex patterns. Deeper networks with more layers can capture hierarchical representations, while wider networks with more neurons per layer can capture more complex interactions within the data. Sixthly, we have information flow. The hidden layers process the input data hierarchically, with each layer transforming the representations learned by the previous layer into more abstract and meaningful representations. This hierarchical processing enables the neural network to learn intricate patterns and relationships in the data, leading to better performance on complex tasks. Lastly, we have the output layer neural network. The output layer of the FNN is where a final prediction or output is generated based on the processed information from the hidden layers. It plays a crucial role in generating the final output, applying appropriate activation function, and computing the loss to guide the training process towards better performance. So, like the last layer, we have the weighted sum calculation. Here, the output layer receives input from the neurons in the preceding layer, and each neuron in the output layer calculates the weighted sum of the outputs of the neurons in the previous layer, with weights representing the strength of the connections. We also have the application function in the application, but we discussed this in the previous layer, so we won't go any further here because it's the same. Thirdly, we have output generation. After applying the activation function, the neurons in the output layer produce the final output or prediction of the neural networks. In regression tasks, the output of the output layer directly represents the predicted numerical value. Fourthly, we have our loss computation. The output layer is compared to the ground truth labels or target values using a loss function. The loss function measures the discrepancy between the predicted output and the actual output, providing a quantitative measure of the model's performance. Fifth and lastly, we backpropagation update weights. The error computed by the loss function is then backpropagated through the network, starting from the output layer and moving forward through the hidden layers. The weights and biases of the network are updated iteratively using optimization algorithms such as gradient descent to minimize the loss function to improve the accuracy of the prediction. Thank you so much for watching. I hope you have a great day. And here is the source I used.